The common method for calculating a determinant relies on cross-multiplying numbers in a grid. Instead of mere arithmetic, this entire mathematical architecture actually adheres to a much more precise underlying structural logic. In Kenneth Hoffman and Ray Kunze's linear algebra, this is defined rigorously. The determinant is an alternating n-linear function. Sections 5.3 and 5.4 of the text detail the combinatorial mechanics that govern how this function operates. This study requires moving past calculation and toward an analysis of mathematical structure. Mastering the mechanics of permutations is the necessary prerequisite for utilizing the determinant's mathematical properties. The foundation of this system is the permutation. A permutation, sigma, is a specific rearrangement of the integers 1 through n. The complete collection of every possible rearrangement of that set forms the symmetric group, Sn. For a set of n elements, there are n factorial distinct permutations. A 3x3 matrix generates 6, while a 5x5 generates 120. Every permutation in the group possesses a specific sign, or parity. When an arrangement is reached through an even number of swaps between pairs, it is an even permutation. It is assigned a sign of +1. Arrangements requiring an odd number of swaps are odd permutations, carrying a sign of -1. Parity dictates the sign of the determinant's terms. The Leibniz formula defines the determinant as a summation across every permutation. This imposes a strict constraint. Each term is a product containing exactly one entry from every row and simultaneously exactly one entry from every column. In a 2x2 matrix, the identity permutation targets the main diagonal. With 0 swaps, it is even, entering the summation positively. The only other permutation requires 1 swap, selecting the anti-diagonal. 1 is odd, making the sign negative, which completes the standard 2x2 formula. While the 2x2 case is simple, the complexity scales factorially. A 3x3 matrix requires 6 terms, a 4x4 requires 24. This combinatorial expansion is ordered and controlled by the strict parity rules of the symmetric group. Section 5.4 shifts focus to the determinant's behavior as an alternating n-linear function. This structural definition proves several operational properties, such as the fact that the determinant of a matrix equals the determinant of its transpose. Because the summation systematically pairs rows and columns, they exhibit perfect symmetry within the function. This symmetry validates row operations. Adding a multiple of one row to another leaves the determinant's value unchanged. The alternating nature of the function means any matrix with 2 identical rows evaluates to 0, as the permutations cancel one another out. These rules are evident in a triangular matrix, where entries below the main diagonal are 0. Applying the permutation formula, any sequence deviating from the main diagonal selects a 0, nullifying the term. Therefore, the determinant is simply the product of the main diagonal entries. This structural rigidity also yields the multiplicative theorem. The determinant of the product AB is equal to the product of the individual determinants. To evaluate a 4x4 matrix through a raw expansion, one must calculate 24 terms and track 24 signs. Using row operations to reach a triangular state reduces this to a single multiplication of the 4 diagonal entries. Utilizing these axiomatic properties converts a factorial combinatorial task into a logical deduction. The determinant is the systematic output of the symmetric group of permutations. The mathematical parity of those permutations provides the mechanism for the positive or negative sign of every term in the matrix expansion. This n-linear structure is what allows for operational shortcuts like row reduction. Advanced linear algebra prioritizes structural understanding over brute force calculation. If you found this helpful, like the video and subscribe for more clear explanations from Hoffman and Kunze linear algebra. The determinant serves as evidence that mastering axiomatic structural rules provides the most efficient tools for mathematical analysis.